So this is 5.2, exponential functions and graphs, and the only thing we're doing in this section is graphing exponential equations and exponential functions. And so here are three examples. This is f of x equals 2 to the x, and this is exponential growth. F of x equals 1/2 to the x power. This is exponential decay. And f of x equals some number, 3.57 to the x power. This again will be exponential growth. And so what determines whether it's growth or decay is if you have a function with a base to the x power. If that base is greater than 1, then you have growth. And the bigger the base is, the faster it grows. So something like 2 to the x grows kind of fast, 4 to the x grows faster, and 10 to the x grows really fast. The base of the exponent dictates how quickly it grows. So these are all growth functions. On the other hand, if you have a base that is in between 0 and 1, that's exponential decay. And these graphs decrease over time. When you have something like 2 to the x power, for every iteration you're multiplying by 2. So 2 times 2 is 4, times 2 is 8, times 2 is 16. If you take something to the 1/2 power, and remember 1/2 is in between 0 and 1, if you start out with a number like 32, you multiply 1/2, multiply 1/2, multiply 1/2, multiply 1/2, your number gets smaller for each iteration. 16, 8, 4, 2. Another way to think about it is to say you're dividing by 2. Divide by 2. Divide by 2. So in exponential growth, you multiply every iteration. You multiply by a number. In exponential decay, you divide by a number each time. So if you have a base of 4, instead of 2 to the x, if you had 4 to the x, that means every iteration you're multiplying by 4. And that number is going to get very big very fast. If you start out with 1, so you get 4, 16, 64, times 4 is what, 256, times 4 is 1024. This is the first one that we looked at. This is 2 to the x, and what we want to do is graph it. So one way to do this is to pick a bunch of x values, 0, 1, 2, 3, -1, -2, -3, and plug them into the function. So this would become 2 to the 0 power, which is 1. 2 to the first power, 2 to the second power, 2 to the third power. Now this is where things get tricky. 2 to the -1 is 1 over 2. Remember that negative values reciprocate. They flip it. So 2 to the -2 is 1 over 2 to the second, which is 1/4. And 2 to the -3 is 1 over 2 to the third, which is 1/8. What this creates is a list of y coordinates. You can then take your x coordinates and your y coordinates and put them together as ordered pairs. And then you can graph your x coordinates on the x-axis, you can graph your y coordinates on the y-axis, and you create a graph like this. So this is the graph of 2 to the x power. One important point that you want to note on this graph that every exponential goes through is the point 0, 1. Every exponential goes through that. We'll say this is the anchor point that every generic exponential goes through. So this is f of x equals 1/2 to the x power. We're going to pick some x values, and we're going to plug them in, and we're going to generate some y values. So if you wanted to do this, you could say 1/2 to the 0 power equals 1. 1/2 to the -1 is 2. And how did you get 2? Well, you said that that is 2 over 1 to the first power. Remember, this negative exponent reciprocates the 1/2. It flips it. And if you take a look at the next one, this is 1/2 to the -2 power, which is 2 over 1 to the second power, which is 4. The point that they're making off to the left is that this thing, 1/2 to the x, is equal to 2 over 1 to the -x. which is 2 to the negative x. 1/2 squared, which is 1/2 times 1/2, which is 1/4. And this is 1/2 to the third power, which is 1/8. So then you take these values and you plot them, and you get a graph that looks like this. So this is an exponential decay, and even though this is decay, it still goes through the point 0.1. So exponential growth goes through the point 0.1, exponential decay goes through the point 0.1. So this shows exponential decay and exponential growth. So you can see that 0.25 is the smallest number, and that graph decays the quickest. It has the steepest negative slope. 0.4 is the next steepest, and 0.7 doesn't decay very fast at all. So this red graph does not decay very fast. As a matter of fact, as your base approaches 1, the rate of decay slows down. So if you want something to decay really fast, you want a very small number. You'd want like 0.01 to the x power. That will decay incredibly fast. Why will it decay incredibly fast? Because this is 100th to the x power. That means every iteration you're dividing by 100, dividing by 100, dividing by 100. This is 1/4. So the yellow graph from this step to the next step divides by 4, divides by 4, divides by 4. What decreases faster, dividing by 4 every iteration or dividing by 100 every iteration? Dividing by 100 decreases, it decays much, much faster. When we look at the growth, you can see the same thing. We have 1.8, 2.5, and a 4. Which one's going to grow the fastest? Multiplying by 1.8 every step or multiplying by 4 every step? Multiplying by 4. If every week your check got multiplied by a number, which number would you want it to get multiplied by? The 4. Multiply my check by 4 every week. Don't multiply my check by 1.8. That doesn't grow as fast as multiplying by 4. So this is y equals 2 to the x minus 2 power. And this comes from the generic format y equals a base to the x minus h power, where h is your horizontal shift. So if you wanted to graph this, you just kind of sketch a graph, and there's one point that we're going to put on here for certain, 0, 1. That's the point that all these graphs go through. But this graph has a shift on it. It has a horizontal shift, and in our case, the horizontal shift is 2 units to the right. So that means using our anchor point, we need to go 1, 2 units to the right. 1, 2. So now our anchor point is no longer at 0, 1, it's now at 2, 1. And so originally we had a graph, this is exponential growth, the base is at 2, so that means originally our graph would look something like this. But now we have this horizontal shift, 2 units. So that means every point on this graph is shifted 2 units. And so now our graph looks something like this. And this would be the graph of 2 to the x minus 2 power. That's what it looks like when you plug it into a computer. This is written to you in 3 different ways. Method number 1, a decimal. 5 minus 0.5 to the x power. Don't like the decimal format. Format number 2, fraction format. 5 minus 1/2 to the x power. Not too bad. Format number 3, negative exponent power. 5 minus 2 to the negative x. Of these 3, which one do you want to work with? Green, I don't really want to monkey around with a decimal. 0.5, 0.5, 0.5, yuck. And I really don't want to monkey around with that negative exponent. Both of those are trouble spots, right? They sort of unnecessarily complicate it. Now, if you're a student that loves decimals, go with the green. Great. And if you are totally fine with reciprocating base and going with negative exponents, go with the blue. But I kind of like the yellow. So we're going to talk about this one in terms of the yellow format, right? So let's start with 5 minus 1/2 to the x power. So first, let's talk about 1/2 to the x power. Just look at this first part, and we'll call this part A. What does 1/2 to the x power look like? Is it growth or decay? It's going to decay. So if we draw a generic decay function, remember this is the point 0, 1, and if we wanted to pick another point, we could pick -1, and it's going to go through -1, +2. Okay, so this is A. Now let's add on the negative. This point here, -1, +2, gets reflected down here to -1, -2. And this point 0, 1 gets reflected down here to become 0, -1. And this is the function -1/2 to the x power. So our final step is step C, add 5. So -1, -2 moves up 5 units. And this gets moved up. So now we have a point here, 0, 4, and we have another point here. Things are getting crowded. That point right there is going to be -1, 3. And so now we take this function, the orange function, and we shift everything up 5 units. We're adding 5 to it. Part A is the red graph, which only did 1/2 to the x power. Then we applied the negative, which flipped it about the x-axis. It made all your positive y values negative. And then we took that graph and we shifted it up 5 units. That's the function we were given, right? And your question is, what if you put a negative in front of the x?
Yeah.
I don't know what's going to happen. Let's find out. So I'm just going to copy this guy. Can I paste them right here? It flipped it over the y-axis, right? So basically, if you take all your x's and you make them negative x's, it'll flip it. Wow, this is good. This is real good. What's happening here? Tell me about the red graph, or maybe I'll tell you about the red graph. The red graph is f of x equals 2 to the x minus 2. Now, if you get rid of this shift, what type of graph is the red graph? It's growth, right? It's exponential growth. What kind of graph is the blue graph? Decay. Well, how can it be decay? Well, let's look at the function. So the blue function is f of x equals 2 to the negative x minus 2. And again, let's forget about the shift. That is 2 to the negative x, which is 1 over 2 to the x, which is 1/2 to the x power. Decay. E is a very special number in mathematics. They don't tell you why, they just tell you it's special. It's named after Euler or Euler, depending on your pronunciation and dialect. And it represents 2.7. So every time you see E, think of 2.7. It's an irrational number like pi, which means it never ends and it never repeats. So E is kind of cool like pi. So here are some decimal equivalents of e to the x power, and these are done with a calculator. This guy is exponential growth because it's 2.7 to the x power, and this guy is exponential decay because it's 1 over 2.7 to the x power. So e with a positive exponent is growth, e with a negative exponent is decay. E to the x, a nice exponential growth, e to the negative x, a nice exponential decay. Here's e to the x plus 3. E to the x plus 3 power. So let's graph it. What point do we want to put on as an anchor point? 0, 1. And this is exponential growth. So it's probably going to look something like this. This is what e to the x looks like. And now we want to put on plus 3. And so plus 3 is going to be a shift to the left. Shift it 3 units left. So 0, 1, we're going to move you 3 units to the left. So you now become negative 3, 1. And then we're going to just shift everybody to the left, and we'll get a graph that looks like this. This is what you get if you plug it into your computer. Here's e to the negative 0.5 of x. So if you were to rewrite this, this is e to the negative 1/2 times x, or e to the negative x over 2. Another way we could write this, if you wanted to, remember what negative exponents do, they reciprocate. So this is 1 over e to the x over 2 power, which is the same as 1 over e decay to the x over 2. So this is going to look like a decay function. It's going to go through 0, 1. So here's the point, 0, 1. And an everyday decay function probably looks like this. But this decay factor it's got a 1/2 out in front here, which means that everything gets multiplied by 1/2. It's a scaling factor, like a stretching factor. And so that means take this point and multiply it by 1/2, and multiply this by 1/2, and multiply this by 1/2. It still goes through here. 1/2, 1/2, because if you put in 0 over 2, it's still 1. 1/2, 1/2. So this is going to be kind of scaled down. It's going to be crunched down a little bit. Regular e to the x goes like this. If you multiply this by a 1/2 scaling factor, all of these points are cut in half. So if we wanted to do this one, again, we want to break it into parts. So we've got 1 minus e to the negative 2x. And so you want to start by looking at e to the negative x. That's exponential decay. So that means you're going to have a function that decays like this. Then you're going to multiply it by the 2. That's going to double everything. Then you're going to take the opposite of that, and then you're going to shift everything by 1.